today we have Dr. Jacquiline Romero from University of Queensland. Again, for those who are logging for the first time for this quick talk, again, this is also for you, Jackie. So quick, this is a quantum information and coherence talk that we do here. This is supposed to be a very informal tutorial level talk, so that people who are interested can look for something to work on later, or people who are kind of students who are interested in these areas can get more interested, and so that we can have them do PhDs in these areas. So that's the overall goal of this kind of talk series. So for that, again, this will be a very informal tutorial level talk. So everybody just feel free to interrupt Jackie anytime. So with that, let me just a brief bio of Jackie. She's from Manila, Philippines. She has a BS in applied physics and MS in physics from University of Philippines. She did her PhD at the University of Glasgow, and where she continued as a researcher after finishing her PhD. In 2015, she moved to Brisbane to join the Quantum Technology Group at the University of Queensland. In 2016, she took up an ORC-DECRA fellowship with the same group. And in 2018, she won the Ruby Payne Scott Medal of the Australian Institute of Physics for Excellence in Early Career Research. In 2019, she won a L'Oreal UNESCO International Rising Star Grant, one of the 15 awards worldwide. She is currently a senior lecturer and a Westpac Bicentennial Foundation Research Fellow at University of Queensland, where she is continuing her mission to extend quantum information using the shape of light. And the title of her talk today is The Adventures in Hilbert Space, Quantum Information Using the Shape of Light. So Jackie, over to you.
Okay. Thanks very much, Anand, for inviting me to give a talk to your institute. A brief history, Anand actually is one of the first postdocs I worked with when I was a PhD student in Glasgow. Oh, actually, he wasn't a postdoc then. I think he was finishing his PhD.
Yes, that is correct.
Yes, you were finishing, and he visited us in Glasgow. And in the words of one of the postdocs I work with, Jonathan, he said, Anand taught us everything we know about down conversion. So the fact that I'm still doing it to this day is actually thanks to Anand. So I'm really glad to be paying forward the things that Anand taught us then. I hope you'll get something from my talk today. Anand said there are undergraduates in the audience, so I tried to start slow and hopefully give you some more bit of content towards the end. So Anand has introduced me. So hang on. Okay, so he's already mentioned all the people I need to thank for supporting my research: Westpac, the Australian Research Council, L'Oreal UNESCO Foundation. And I am actually also part of EQS, which is the Center of Excellence for Engineered Quantum Systems. Okay, so this is going to be, as Anand said, a bit of an informal talk. I do abide by this speaker guidelines. Okay, hang on. Okay. So I try to make it personal. Make it personable, and I cannot avoid tables and graphs, unfortunately, but I know this is a physics institute, so perhaps you don't care that there are tables and graphs, so we'll just keep on using those. Okay, so this is one of the classic pictures of quantum physicists. Like, you probably have the densest number of Nobel winners in that picture. You've got Einstein, Curie, Bohr. That's what quantum physicists look like before. That's what physicists look like before, probably. But we are now in this era where this is what we think physicists look like. I wonder if it's good or bad. You could tell me. So I'll try to talk a bit about myself, which is this lady here. So that was my first day as a PhD student in Glasgow. That's really the first day of my PhD. That's me midway in my PhD. That's my PhD supervisor there, Miles Padgett. Another PhD supervisor, Steve Barnett, he wrote a book on quantum information. It's a good book. You might want to check it out if you're starting to learn quantum information. This is me on my PhD graduation. This is actually the workhorse of my PhD thesis. That's the experiment that Anand helped us set up in the first place. And as Anand said, I've come from the Philippines. I spent 7 years in Glasgow after my master's, and now I am in the University of Queensland in Australia. And I have now my group. I think some of them are joining us here. So I have Marcos, Michael, Kalmudi, Zhonghua, and Maddie. We have a website. If you want to learn more about what we do, please visit quantumatibapa.org. And today I'm going to leave you with hopefully 3 things. First, I'd like to discuss the difference between classical and quantum information. So this is what Anand was saying, the tutorial level. I'd like to talk about 2 particular recent papers that we published. One is on ignorance, the idea that your ignorance of the whole does not really imply ignorance of the parts of that whole. And the third is actually an experiment that you might be interested in as well. It's on tomography. It's the problem of learning an unknown quantum state. So let me start with the first point here. So if somebody asks you what's the difference between quantum and classical, what would you say? Does anyone want to have a go with that? Just shout, like shout over this drilling background. What, is there anyone who'd like to answer that question? What's the difference between quantum and classical? No one? Everyone shy? Okay, that's okay. Last 5 seconds. Okay, no one really wants to. Yes.
Yeah, hello, Jackie. Can you hear me?
Yes.
Yeah. So quantum world is let's like a probabilistic, and classical world is certain.
Okay.
So that's the first difference we could.
Yes. Okay. So that is actually true. So quantum is probabilistic. Classical is deterministic. A lot of people would subscribe by that. In terms of information, that's the difference. It's you have in classical information you have deterministic properties. In quantum, we don't have that. And the boundary between this quantum and classical is sometimes people would say it's the size, it's the energy level, it's the like something physical, but really at the very basic level, to me, it's really the information that is the difference. So that's what I'll try to like do for this part of the talk, like really dissect that idea of the difference between classical and quantum information. So information, of course, as we know it, is information like this, you know, Twitter, Facebook, fake news. But all of that, underlying it, there is a physical system. So information, even if it's abstract in our heads, it's a physical thing because there is a physical system that encodes that information. So one example is perhaps when you were little, you'd be playing with these telephone cans, like you'll have your voice vibrating the string that's connecting those cans, and so your playmate could hear what you're saying. So there you have your information that's in your brain being transferred through this physical system, and then it gets transmitted to another person. So it's a very physical system. Information is very physical. And the systems that we know these days, of course, uses, you know, analog and digital information, perhaps more the digital information. So this is encoded in bits, the zeros and ones that we know. And that is the simplest classical system that we have, the bit. So you could think of that as heads and tails. You could think of that as spins, so spin up or spin down. So you have +1, -1. Or you could think of spinning particles, like clockwise, anti-clockwise. Like for the sake of this talk, you could just really think of spin up or spin down. And like these systems here, this is what we would normally refer to as qubits, because they're like quantum things. So we call them qubits, the quantum version of the bit. So how are these different? So how's that spin different from your classical bit? So I would represent a spin like that. So I'll represent it as a vector. We'll think of it as something that we could do experiments on. So as you know, a vector will have both a magnitude and direction. It would have components. So it's like the shadow projected onto some axis would be its components. So I could imagine an apparatus which would be measuring the component on the vertical axis. So this one is just some apparatus, which will measure the component on whether it's up or down. So I could imagine doing that experiment and looking at this window here at the result of my experiment. So say, for instance, if I do that, I get a +1. So I know the spin now has component +1 on this direction. I will then, this apparatus, I will try to like rotate it, flip it along the vertical. So then as expected, the +1 now becomes a -1 because you've turned the apparatus 180 degrees. So that's all good. That's behaving as expected. So behaving as expected, as in spin, is acting like a vector. So I write that as my sigma z, and the result of that experiment is a +1. So the next experiment I do, I have this apparatus, I turn that to 90 degrees. So now it's like I am getting the component along this axis. And I do that experiment, I will get a +1 or a -1. And what you would expect after measuring a sigma z that is +1, if you directed the apparatus in this direction, of course, you would expect that sigma x will be 0 because you already have a +1 on the z direction. But then if you do this experiment on a spin, like this quantum object that is the spin, instead of getting a 0, you get mixed results, which is sometimes +1, sometimes -1, totally random. And that's really surprising because we already thought, well, that's going to be 0 because if it's a vector, then you already have +1 on this z component there. So in this instance, actually, the best that you could do to predict the results of this experiment is to guess randomly, like guess randomly between +1 and -1. And that's actually quite interesting because guessing randomly in classical information is what you would really call as ignorance. Like guessing randomly is ignorance. But you have here a situation where it's really the best that you can do. It's really the best that you know about the system. The greatest chance you will predict the results of this experiment if you just guessed randomly. And that's already a bit of it's a big difference. It's quite interesting. So we have here an experiment where, as you know, one of you said earlier, determinism breaks down, but it is breaking down in a very particular way. If you have many repetitions of this experiment, what you would find is that the number of the +1 measurements will be the same as the number of the -1 measurements. The average would still be 0 as we expected for a classical vector. And the way that we explain this in quantum physics is really very hand wavy. Like experiments, they're never gentle. So the act of measuring would change that system. And also you might have already guessed, that this spin that we're talking about is a very peculiar vector. It's not like your usual displacement vector. It's not your usual momentum vector. It's a very special kind of vector. And that breakdown of determinism has some repercussions in information. Like for example, when we think of Boolean logic, like what we've learned when you maybe took philosophy or I don't know, elementary computer science, when you think of logic, for example, so you have these two propositions. So first proposition, the speaker is wearing a blue shirt. That's going to be true because I am wearing a blue shirt. The speaker is wearing black shoes. That's false. I'm actually at home because I have plumbers in the house. So sorry for the noise. But that's false. I'm not wearing black shoes. So I have here two statements. I can assign to them two truth values, 1 and 0. And in Boolean logic, what you could do is make a truth table of the values for A and B, and then do the operation A and B. And you get this nice table of A and B. And that's all good. You can repeatedly test these two propositions, A and B, and you will get the same answer. Now, what happens now if the propositions that you have pertain to these spins that we were talking about earlier? So for example, your first proposition, the Z component of the spin is +1. And then you have second proposition, the X component is +1. Okay, so let's try to do that experiment again. So you do your experiment, you measure the Z, you get a +1. So A is true, A is 1. You do the X measurement, you get a +1. So you do A and B and the result is 1. All good. But then because you're a good experimentalist, you do the experiment again. So you measure along the Z, you get a +1. You measure along the X, so it's A equals 1. You measure along the X and this time you get a -1. So the proposition B is false. You assign it a value of 0. So now the next time you repeated your experiment, as you can see here, you got a different value of A and B. So you cannot do Boolean logic as you do for classical information when you're talking about spins. And this is actually really something that is very much connected to these two statements here. So this one is, if you'd recognize it, it's the uncertainty principle. So you have here in quantum physics, you have two propositions. So say proposition A, the particle has position X, and the same particle has momentum P. So you have these two propositions, and these two propositions are not confirmable. It's just not possible to do an experiment that will tell you the truth value of this statement. And that's your Heisenberg uncertainty principle. It's coming from the fact that logic sort of breaks down. Like you must have heard of it arising from complementarity and things like that, but it's really very much connected to information and logic and this indeterminism that we have. So what's the difference in quantum physics? So as we've said, experiments, they're never gentle, like we've seen our Z and X experiments. We have quantum states that behave like they're very peculiar vectors. We'll talk about that a bit more later. So they're represented as this state, which is superposition of two vectors. and alpha and beta are complex numbers. And that's really where a lot of the magic comes from, that alpha and beta are complex. Real and imaginary parts, just like life. Okay, so if you're interested in learning more about this, I really recommend reading this book. Like, it's got a YouTube lecture series as well. Leonard Susskind it's really him giving lectures on quantum mechanics, and he's written a book based on that set of lectures. This really is the best start that I have found. So if you're interested, really highly recommend that book. I think it's really a better start than Sakurai, for example, who starts talking about entanglement. Or if you read popular quantum physics books, they might start with the Schrodinger's cat, which is both dead and alive. Or if you start with the historical text of quantum physics, what they'll do is probably start with calculating the levels of the hydrogen atom. So these are all really good, but I think this is the most interesting, really starting from the basics. So yeah, if anyone's teaching quantum physics, this is a good one for undergrads. Okay, so that's the first part. Now the second part, I'll get to more details. So this is an experiment that we did where we've shown something really weird, that the ignorance of the whole does not imply ignorance of the parts. So as you might have guessed, of course, in order to test something like that, we have to make quantum states. So quantum states, you can make them using trapped ions. You can use superconductors. You can use atoms. For our case, we make quantum states using using light, using photons. You could choose from many degrees of freedom. You can use polarization. You can use wavelength or frequency. You can use time bins. For our group, we focus on using the shape of light. That's why it's adventures using the shape of light. And that's really fun because you've got a lot of shapes to choose from. So here are just examples of some different shapes. So each of them would be a set of modes that is a solution to the wave equation. Like, depending on what coordinate system you're using, you'll get Hermite-Gauss for the rectangular, Laguerre-Gauss for cylindrical, and you have Ince-Gauss for everything in between. So you have a lot of different families to choose from, and you could use that to encode information. So in the sense that I could replace the vectors 0 and 1 with shapes of light, like that. So that's your qubit. That's the cat that's both dead and alive. And the good thing about shape is that you've got a lot of shapes to choose from. So you're not limited to a cat. You could have as many animals as you want. You just replace those vectors with your different shapes. And that's why I named my group QDITs at UQ, because this is what we do, like perhaps what Anand does as well. We encode information using the shape of light. So a lot of the work that I did in my PhD was actually to show that shape is a good system to encode quantum information. So we did a lot of tests showing that shape behaves in a quantum way, inequalities. Conclusion from all that study is that you can measure the shape of single photons really well, and we can use it for quantum information. Like this one is actually worked with Anand back in 2008. So going back to this part, so ignorance of the whole and ignorance of the parts. So this was actually a paper that I found interesting 10 years ago because it had a cartoon. It's the first PRL that had a cartoon in it. And I wanted to do an experiment back when I was in Glasgow, but it was just so busy there with other things. So I'm glad I finally was able to do that when I moved here to UQ. And it was actually great because it was the perfect team to do this experiment. So Sally here is actually a philosopher. She like philosophy and physics. Like she had a lot of experience decoding all the proofs for this paper here. So in the end, it was actually very good that I managed to do it just 2-3 years ago with Michael, Sally, and Andrew. So Michael is the PhD student who did this experiment with me. So it was actually a fun experience publishing that paper. Like we got rejected twice, I think. Like there was a referee which really hated us. But that's good because I think with the additional revisions, it was a much better paper. Like the second review that we got was so good that I'm underlining every word of it. So it's a very nice real world interpretation of a statement that comes from pure probability theory, which is accessible to non-experts. So I'll try to test that statement today. I hope you'd really appreciate it, even if you're non-expert. Okay, so that was published last year. So if you need more details, the paper is here. We made it to the cover with our pretty pictures there. So that's the phase of the light that we were using. We have actually, we also have some coverage from Eureka Alert, so you could check that one out too. So the details, well, I'll talk about in the next few minutes. So first is we have to be clear what is whole and what is parts. So when you think of quantum states, the whole usually you imagine that as your entangled pair, like the information that is encoded in the pair of particles that's entangled. That's the whole. And the parts would be one particle. So the particle that was separated, each one of that is considered a part. In our experiment, we actually were very old school. We didn't use entanglement. What we used was a dit string. So a dit string, let's call that Y. And it would be a concatenation of Y0 and Y1. So this one, Y0 and Y1, those are the parts of the whole. And how does dimension come in? How does the dit come in? Well, as you would expect, as dimension increases, it becomes harder to guess the phase of, it becomes harder to guess what the value of each part is. It's like having a die that has different number of faces. As the number of faces increases, it becomes harder to guess which face it would land on. So that's our whole and parts. And it's really, this cartoon here really sort of sums up our experiment. We did this dit string many, many times, and we showed some measures of randomness. Okay, so that paper there, the paper with the cartoon, has a very important inequality, which is called the min-entropy splitting inequality. So what it says is that for any random variable y, so for any string, which is y0, y1, so this is the string, you have a system that encodes that string, let's call that E. So given that string and the encoding E, there exists a random variable C, which is 0 or 1, such that this statement will be true. So this, okay, hang on. So this is this is like the entropy of a part C, and this is the min-entropy of the whole. So it's like this inequality is essentially saying the ignorance of a part should at least be equal to 1/2 of your ignorance of the whole. So that's what the min-entropy splitting inequality is. It's like the entropy of the part, you split the entropy of the whole. And in the scenario, that cartoon, that in that paper, their scenario was like this. So you have a student who is going to take a test. He's got a cheat sheet, which we'll call E. And there's a teacher who just asked the student, what is Y1? What is Y0? So the scenario is there's a test that the student comes to. They have an encoding E. And then the teacher just always asks, what is Y0? What is Y1? Just does that over and over. Now the C is the pointer to the part that the student doesn't know. So this inequality essentially says, yes?
Yeah, so maybe I missed it. So did you define ignorance, or the entropy you're taking as ignorance? Or, I mean, I probably missed that.
So the min-entropy is what we take as the ignorance.
Okay, thank you.
Yeah, like I hope it would be clear in the next. So in the next slides, I'll talk about it in terms of guessing probability.
Okay.
I think it will be clear there. So what this theorem says is that there exists a pointer. So the teacher can always point to the unknown part, to the part that the student doesn't know, by just doing this test over and over. Like, it's the teacher has a task, like has an exam, and in doing that exam, the teacher could find whether the student doesn't know the first part, the first character, or the second character. So in classical information, there is always a test that you could do to find that pointer, to find C. So meaning your ignorance can always be uncovered, something like that. So in terms of probability, so I hope this will be clearer. So in terms of probability, this is what it looks like. So you have a string, Y. So like, think of it as you have entries in a page. Like you could choose any of these values for your Y0 and Y1. So each instance of the string is like these small letters here. So for each instance, you have Y0, Y1. And you could choose Y0, Y1 from any of these values here. So you have d possibilities for that string. Like, so you have d squared possible strings. And I have an encoding, let's call that E, which is just these nodes here. And then so you have an encoding, you have the possible encodings that you have. And then the teacher will do a test. So in this case, let's call it a measurement. Like you could find out whether the student has the correct answer or the wrong answer, like the probability that the student will get it correct or not. So in terms of probability of guessing, so you have probability of guessing YC, given that the student has E, encoding E, and the teacher asks for what is Y sub C. And the same inequality could be written like this. So the probability of guessing is always bounded by 1 over square root of D. If it were if it were a classical cheat sheet, a classical encoding, the best probability of guessing is 1 over square root of D. And that just comes from this here. So how does the teacher then spot the ignorance? How does the teacher find out what the student doesn't know? So I think it helps to consider the optimal classical strategy, which is this. So what you do is you always encode just one part of the string. So say I always encode the second one. So every time the teacher asks what is the first character, you always get it correctly. But because you don't have the other one, you just guess it randomly. So this is your best guessing probability if it so happened that the teacher asked for the Y1. But if not, then you have the worst guessing probability, which is guessed at random. It's 1 over D. So in order for the teacher to find what is the part that is unknown to the student, you just have to find the part that is being guessed at random. And as you can see, that follows the inequality here. Like it's less than 1 over square root of d. So now that PRL paper from 2011 asked the question, what happens when your encoding is a quantum encoding? So instead of, say, just putting in either the first or the second character, you have a quantum strategy, and that is to encode this special quantum state here. So this X and Z are just higher order Pauli matrices. So it's like, you don't have to focus on it much. It's just the qubit encoding that the authors use to show that you could violate that inequality. So this is the qubit encoding for your 2-dit string. And that's what we did in our experiment. So here, what we have is the scenario of a student and the teacher. So we translated that to an simple experiment like this. So we have the encoding that the student brings is encoded in one of the SLM. So we call that E. And then the measurement is on the second SLM. So this is the M part. And the encoding here, you could just follow the equation I gave in the previous slide. Functions have states like let's be accurate. So the probability distribution of the photon position will look like this. So these are the different shapes that you could get if you follow that prescription for what psi is. And then the test would then be as simple as really taking the overlap of what the teacher is measuring and what the encoding is. So the probabilities are obtained like in this way. So I know you would be asking now, well, hang on, that's not a really single photon source. And that's actually true. We didn't really use a single photon source. So we were very careful in our paper. We asked the help of Gerard Milburn, actually, like Milburn of the KLM, the KLM protocol. So we were wondering what would be the error in the probability because we were not using single photons. And it turns out, if you were using these coherent states that were like weak coherent states that we were using, you could work out the fidelity, meaning the difference between the state, the probabilities that you're expecting and the probabilities that you get in the experiment. So in theory, you would miss by this much %. So this is the best that you could do if everything were perfect. This is the best you could do just because you're using not a real single photon source. So we look at this and then we thought, well, that's not too much. So we can continue our experiment using this weak coherent source because the errors we will get will not be that much. So we did that, and if you use those encodings, you could actually calculate the guessing probability for part 0 and part 1. And what you'll find is that, hey, they're equal. So the guessing probability for either part will now be the same. There is no part that is, there's no part that's being guessed randomly. There's no 1 over d. And that makes it hard for a teacher to find what is the part that the student doesn't know because it's not apparent, nothing is apparently guessed randomly. So if you recall again the theorem in terms of the guessing probability, you have that. If you just substitute these guessing probabilities, you'd find easily that this inequality is now violated. So what it shows you is that there is no test that can reveal what part you don't know, the student doesn't know, if the student did use a quantum encoding. So there's no test to find that C in quantum information. And the other interesting thing as well is that the student can score higher with a quantum encoding. So for example, this is the classical optimal strategy. So let's assume half the time the teacher will ask for part 1, half the time will ask for part 0. So the score that you get for 2 dimensions is about 75%. For a quantum strategy, you do the same thing. So you just substitute those guessing probabilities and you get a higher score. You get 85%. If you go to 6 dimensions for the classical strategy, so you just, again, always just put the first part on your cheat sheet, you get 58%. For the quantum strategy, you get 70%. So that's also quite interesting. So, and this is the graph which really tells you there is no test that will reveal which part the student doesn't know. So this Q is the probability that, so this Q is the probability that the teacher asks which part. So say if it's 0, the teacher will always ask from Y1. If it's 1, the teacher will always ask from Y0. And for the classical strategy, as you could see, the probability really depends. The probability of guessing really depends on what the teacher is asking. But if you are using a quantum encoding, all of a sudden that probability becomes uniform, regardless of what the teacher is asking. So this is for 13-dimensional system. So this is about 64%. So it becomes independent now of what part is being asked. So to summarize that part, so for a qubit encoding, the student can get a higher score and the teacher cannot point to the part that the student is ignorant of, because suddenly you lose the part that's being guessed as 1/d. It becomes uniform guessing probability for either part. Okay. So I have some more minutes left. I'll talk about another experiment that we did, which is actually a very similar setup. And this time it's about learning the quantum state. So this work is done with Marcus, Maddie, Andrew, and Chris Ferry. So Chris Ferry, you might recognize him as the author of the book series, Quantum Physics for Babies. So he's the theorist we work with. So this work is about tomography. So tomography, like you might realize, no, tomography is about finding what an unknown object is by taking many slices of that object. Like a CT scan, for example, would be is tomography. So we have tomography for quantum states as well. And the work I'm going to talk about is something that makes it easier for higher dimensional systems. So the question we deal with is what is an unknown quantum state psi? So let's motivate that a little bit. Like, why do we need to do quantum state tomography? And why is it not enough to do it just for a few qubits? So this is a really interesting graph, a bit of a depressing graph actually. So this is a graph which shows you how many logical qubits you need in order to factor a number, an L-bit number. So this one is actually what the NIST recommends as the securest, most secure length of the key. These graphs, these lines, these are quantum computing algorithms applied to factoring. This line is what a classical computer can do. So for example, here you find so a classical computer could do factoring in 1 hour. And the equivalent for that would be for something that could be done in 1 hour by a quantum computer, you'll need about 2 times 9, you'll need about 2L squared. So 2 times 300 squared qubits. So it's a really big computer in order to be right now. And if we are to build a computer like that someday, we might want to characterize that computer. And that would most probably involve characterizing that number of qubits. And that's a really difficult problem. So that's where quantum state tomography comes in. We have to know whether the quantum computers are, the qubits in your quantum computers are prepared in the way that you want them, whether the operations that acted on them operated in the way that you want. And for that, you need quantum state tomography. You need the description of that system. So whether you're working with ions or photons or really any physical system, that parameter space will grow. So for example, if you have a row of ions, n ions, you'll have a parameter space that's 4 to the n minus 1. If you have qubits, like what we have, the parameter space, so in terms of d, it would grow as d to the 2n minus 1. So it's really an exponential scaling that you have. So in quantum state tomography, the objective is to get rho, the density matrix rho. So it's just a matrix that would describe your quantum state. So you have here an unknown quantum state. It's generating data. And we don't usually say this, but that data needs to be saved. And from that saved data, you try to find the best guess for rho that would explain all the probabilities that you got. And that's usually done in post-processing. For example, you have maximum likelihood, which is order d to the 4th in terms of the computation power that you need. And that is good, but it could be computationally expensive. If you have a big system, it's done in post-processing. And because you're dealing with probabilities, it will be sensitive to noise. So Chris Ferry, our collaborator, many years ago, proposed a way of tomography which has no post-processing, it's efficient, and it's robust. And that's what I hope I will convince you about in the next few minutes. So this tomography is called self-guided tomography. So the details are in this paper here. So what it's like hopping in this Hilbert space here. So you have an unknown target state, let's call that psi. You start with an estimate, so we call the estimate sigmas. And from the current estimate, you choose a random direction to measure in. So you measure these two states here. So by the way, so these are, I'll talk about pure states. So these are pure states. So I'll measure these two states here. These are just, so the betas, they are hyperparameters that we've simulated before we did the experiment. So we tried to optimize them. So from the measurements, we calculate the gradient, and then that gradient now defines what the next hop would be. So note that F is it's in our case it's an overlap. So it's the overlap of sigma to the unknown state, but any distance measure will do. Anything that could be estimated from your experiment. It just so happened this was a convenient thing for us to measure. So from there, once you've got the gradient now, you could then define the next estimate. So again, the alphas here are hyperparameters that we've simulated before we did the experiment. And then you just do over and over, repeat until you get the fidelity, you get the fidelity that you want. So I've talked about this earlier already, so you won't be surprised that we use the shape as our qubits. So for example, for a qubit, we use these Laguerre-Gauss modes here. So L is the number of twists qubits in one cycle. P would be the number of the phase discontinuity along the radial direction. So that's just the intensity and the phase. So Q-quints, we have this set of modes here. Q-vigent, I wasn't able to list them all, but this is an example of a superposition from the 20 modes that we've chosen as our basis. So the experimental setup that we have is actually very similar to our ignorance experiment, because in the end, what we need are these overlap measurements here. So we have here the psi, and we have here the sigma. And then from there, we get the counts from, so these are the counts from the two random directions that we chose, the plus and minus. And then from there, we decide what would be the next update. So note that these are not probabilities. We're just measuring counts. And that actually is important for robustness, because as you would, if you've done experiments like this, what you'd find is that depending on the mode that you're trying to measure, sometimes you don't get uniform efficiency. So say, for example, if I were measuring an LG beam that has L equals 100, like I'll be struggling to measure that. It would have a much lower efficiency compared to, say, an LG beam that has L equals 1. So there are those mode-dependent efficiencies that sometimes mess up the probabilities, but because we are not measuring probabilities, these are pseudo-normalized, like we're just using counts, we are immune to those errors. So these are the results for our tomography. So we simulated SGT, the self-guided tomography, for 1,000 states for both Q-trits and Q-quints. And we have here the experiment, which really follows our simulations very closely. So as you could see here on the y-axis, we plot infidelity. So this is 1 minus the fidelity, just so we
Jackie?
see that. Yes?
So with 1,000 states, even 1,000 separate experiments?
Yes, so this is, so like we encoded 1,000 different superpositions of Q-trits and Q-quints.
Okay.
Yeah. So we did that, and we found our infidelity is really, really good. It's really small. And we tried it with a Q-vigent, like with a 20-dimensional state. So vigent, because vigenti is Latin for 20. I didn't think of that word. It was Andrew White, blame him. But do use the word if you ever work on a 20-dimensional state, and reference us. So we did simulations for 200 states for the Q-vigent, and we still found really good infidelity. So that was so here we have a lot of photons here. So it was really about 100,000 photons for each of those experiments. So the next thing we tested was robustness. So robustness, we tested by using less photons. So now we have a higher statistical noise, and we still get a good infidelity. So we're missing like, yeah, we have 98% here, 97%, 95%, which is still pretty good. And the next thing we did is to like introduce some turbulence, like really destroy the modes a bit, see how close we get. And it still worked pretty good. So it's really weak, just weak turbulence. We found the paper. We found the paper, and we just chose. Sorry, what happened? Okay, sorry. Okay.
Yeah, it's back.
Yeah, it's back. Yeah. So we just use this parameter here for weak turbulence, and we showed that it still converges to the state. So we compared that with standard tomography, so what you would usually do in post-processing. So we stop at 60 iterations here, and you find that for Q-trits and Q-quints, there really is significant difference. for the infidelity. Someone was asking a question.
Is there any question? Well, then I can take, I can use this time to ask a question. So regarding your turbulence thing, so turbulence should affect the state itself, right? The incoming state itself?
Yeah. It will so you compare it to the state that you are encoding. But yeah, it will affect the state itself.
Okay.
It would, like what it would do is really, it will give you a bit of mixedness because you'll have the state changing. Like this is for pure states.
Mm-hmm.
Yeah. So we compare that with the standard tomography, and we see.
Oh, okay, okay. So since this method works only for the pure state, you are kind of comparing that if suppose you had a mixed state, how close it would get to the real thing.
Yeah,
Okay.
So the mixed states, I won't have time to talk to, but I'll show a result on mixed states.
Mm-hmm. Okay.
The mixed state details are in the paper, but I'll talk about it a little bit. So here I'm just showing a comparison between the infidelity you get for the self-guided tomography and the standard tomography. And as you can see, you really get lower infidelity with the self-guided tomography. And what's good about it is that the infidelity that you get will always become smaller for as long as you're happy to just keep the experiment going. It would always go down. Like this, you increase the iterations, it would go down. It's really, how long do you want to wait? So this ANAND is a result for mixed state. So this is a mixed state qubit.
Mm-hmm.
So it's like, it's a bit more complicated because first with the SLM, you actually just always produce a pure state. So to do the mixed state, what we did was we almost like tossed a coin.
Mm-hmm.
And then, so it's like depending on the value of that coin, prepare this state. So it's like sampling that distribution.
Mm-hmm.
And then the algorithm, it's like instead of solving for the 3 coefficients for your pure states, you're now solving like 9 parameters in your density matrix.
Okay.
Like, yeah, like the details will be on the paper, but this plot just shows it still works. It's a bit less better than the pure state one, but it still works. So we tested on a variety of purity. So I think we tried from 0.3 to 0.8, and we were still getting, good results. Okay, so the results, as I've said, they're published here in this paper here, and we've got a summary here as well. Okay. So I think that is my time up. So I hope you got something. So first, difference between classical and quantum. So in quantum experiments, they're never gentle. They always interact with your system. And quantum states, they're really represented differently from your classical states. And I hope I convince you that ignorance of the whole does not imply ignorance of the parts. Like we showed that in our 2-dit string experiment. You could hide what you're ignorant of when you're using a quantum encoding. And finally, I showed you an experiment on self-guided tomography, which is doing the tomography for you without post-processing. It's actually, you have this experiment that is learning what the pure state is, but it also works for mixed states, just with some modifications and some interpretation as well, because we prepared the mixed state in a very artificial way, if you call it that. But I think it's still is a mixed state. Okay, I think with that I'll stop there, and I'll be happy to answer questions.
All right, Jackie, thank you so much. So that was very nice, and yeah, at a pace that even I could understand at least some of it, if not all of it. So thank you for that. So now, yeah, so we are open to questions now. So there's one quick question in the chat box. Maybe we can take that first, and then we can go to the, or Srinivas, so you can just, you can just unmute yourself and shoot your question.
Hello.
Yeah, go ahead.
So my question is, how many measurements that you do in the tomography protocol?
How many measurements we do in the tomography protocol? So each iteration here, you measure 2 directions. So like to get to the 100 iterations here, that would be like 200 holograms that we've displayed on the SLM. But in terms of, if you mean measurements as in how many photons we've counted, it's about, for the high count state, it's about 100,000 per shot.
Okay. My question is that if we have a state, superposition state that is coming to your detector, so we want to have a tomography of that. So the state is available to us, and if you do many measurements, whether that state means multiple copies of the given state is not available, then how do you do such measurements?
So yeah, so yes, that's a very good point. So here we could do this experiment because we have multiple copies of the photons. Like if you're doing it on another system, like it really depends on what your system is like, but it's necessary that you need to have copies of that system, or you do some kind of, I don't know, some non-destructive measurement, I suppose. But you'll have to adapt the self-guided tomography algorithm for the distance measure that you need for the algorithm to work.
Okay. Thank you very much.
Other questions?
Yeah.
Yes, second.
Hello.
Yeah, second, go ahead.
Okay, yeah. So I had a couple of questions. It was really nice talk. Extremely, really enjoyed the talk on every aspect of it. So I'm firstly a little confused about the self-guided tomography. So here, the self-guiding, is there some sort of a feedback, or is there a decision for the self-guiding?
So the feedback for the self-guided tomography is really the counts that you get. So let's imagine a much simpler system. Like just say if it's polarization, right? So you have you have an unknown polarization, and then you have a second polarizer that you're just randomly orienting, right? So it's almost like you find the orientation of the second polarizer that would maximize the count. Polarization, we're dealing with these spatial modes. So what you have is you have multiple copies of the state that you're making with your first hologram, and then you have a smart algorithm to encode something on the second SLM that would then maximize the counts, because you will get maximum counts if you have matching holograms for the pure state.
And then the counts are single pixel count on a...
No, yeah, so it's a single mode fiber that is coupled to our single photon detector. Yeah. I mean, there you could probably, I think a colleague at UQ has something that uses a camera, like in one shot, but I don't really know the details, but you could do that with the camera for sure. I mean, Anand probably has done something like it.
And then based on your counts in the APT, your like that MSLM is choosing a basis.
Yes. So based on the counts, you
so that is where the feedback is, right? Like basically, if I close the loop, the SPAD is going back to MSLM.
Yes. So the counts that you gets fed back to the algorithms in the decision to which next point to go to.
Yeah. So then basically I had this question that these are basically distance measures. So these
Yes.
are like Fisher information. Like, can you actually use this for precision measurements and like estimating parameters and so on? Because the state.
Yeah, you probably could. Like any distance measurement will do. It just was convenient for us to really just go with the overlap. But yeah, you could. For the mixed state, for the mixed state actually we used what did we use for the mixed state? Let me find exactly what we used for the mixed state. For the mixed state.
It's quantum relative entropy.
Yeah, it's quantum relative entropy. Yeah, I knew it was entropy. I just couldn't remember the.
Okay.
Yeah, it's quantum relative entropy for the mixed states. And like when I asked Chris why he chose that, he didn't really get a clear answer, except that it works.
I guess one of the answers is that for higher dimensions in the fidelity which we used for the pure states is not unique. So
Yes,
you can
yes.
get different fidelities for like the same fidelity for different states. So you can't use the fidelity anymore. So that's why we moved to quantum relative entropy.
Yeah, that's Marcos, by the way. He's the postdoc that.
I'm Marcus.
Hello.
But then quantum relative entropy, like why quantum relative entropy? There's still a lot of choices. Like
Yeah, they're like pretty much like for
Like
the
it's an
pure states,
information measure, maybe. Like
Yeah.
yeah.
like
Yeah,
for
so
as long as it's unique, every distance measure will work.
Everyone knows. Yeah.
Yeah, well, if you use the usual distance measured, for a mixed state, it gives you very strange numbers. I mean, it gives you a very inflated idea of that you have made a very nice quantum state, even though you have not. So I think this one is probably much better as to how good the fidelity is. Or, I mean, fidelity is not properly, yeah.
Okay, thanks.
I have a few questions
Suman.
regarding, yes,
Yeah, someone go ahead.
regarding self-guiding tomography. Really impressive fidelity. But my question is regarding that sigma you define to measure means some distance measure. Is that sigma is some initial guess you are doing that about the state?
yeah, so
And
you have an initial guess. You have an initial guess, and then the self-guided tomography will be is a way that you could like update to the next guess.
I see. And this how this initial guess is means is that have any effect on the fidelity? Means if I go very beyond from the what the actual state is, means still it can able to come to that convergence.
Yeah, we actually tried different initial states, but it didn't matter.
Okay. And another question I have regarding that some hopping parameters you are using for that feedbacking, that is stochastically some random direction you are choosing. Is that means 1 minus 1 I and minus I? Is this set, this is only the set, or for an d-dimensional state, this should be an d into 1 minus 1 and I minus I number of stochastical parameters you are using?
Hang on. Your question is this one here, whether
Yes.
does this remain the same regardless of the dimension?
Okay, so then if sigma is a d-dimensional state, means how this is being updated in the next iteration? That's my question.
So we just really, so this one is the same regardless of the dimension. It's just you choose directions based on this. Then
So do you have to fix the number of dimension before you start the
yes, yeah, we fix we fix it. Yeah. So it's Yeah, we know the dimension. It's not one of those
So does it need to be exact, or I mean, as long as the dimensionality of the unknown state is smaller than the dimension you're fixing, it should just work, right? It should be fine, right?
We haven't actually tried. Did we try that, Marcos? Is Marcos still?
Well, there are two things to say there. So the first thing is yes, but the second thing, so in theory, yes. In practice, it's a little bit more complicated because if you have a 3-dimensional system or a 4-dimensional system, you would need to use the same state. So the same, in our case, the same value for the OAM, so the L value, and the same P value as well, which generally we don't. So if we increase the dimension, then the L and P values change, like let's say even for the logical 0 or for the logical 1 state, it will have different L and P. So it's not quite as forward in our system because we're trying to keep the GUI phase constant so that basically our mode does not rotate with propagation. So yeah, but in principle, yeah, if you tell the algorithm the dimension is 10 and it turns out the dimension was only 7, it will just put get 0 probabilities for the other for the values where there is nothing to do. And basically in this for this delta that is shown here in the slide, it's like the 1, -1, I and minus I is for, let's say, for a 3-dimensional system. For each of the coefficients, for 0, 1, and 2, it will pick one of these 4 values. So it could be, let's say, 1, -1, minus I to the state it found before, and then it normalizes the same point. Does it make sense?
Yeah. So I mean, I guess then it works the best if the dimensionality of the state is same as the dimensionality of the algorithm being used. But it would work even if the dimensionality of the state is smaller than the dimensionality you're fixing, although in a little contrived way, but it would actually work finally, right?
It should work. You'll get 0 coefficients for some of the, because you define the basis modes at the start. If you have a smaller superposition that you're using, then you should get 0 for some of those modes. Not sure.
Okay.
That would be as efficient, but it should work.
Okay. Harsha.
Yeah. Hi, Jackie. I had a question. Yeah. Hi. So thank you very much. Lovely talk. Enjoyed every bit of it. And and my question was regarding this dimensionality. You seem to have to know it before you begin the experiment. Yeah. No, but actually it's a little more than that, right? For example, I use a 4-dimensional that changes only L values. And I'm looking at the original state, which probably had a non-trivial P value. I will never get to it, right? So what I'm saying, even though the dimensionality would be the same, I still need to know these 2 parameters independently beforehand to begin at all. Or am I missing something?
No, so
what I'm trying to say is that even though the T is same, the LNP content might be different in these equivalent 3-dimensional, the original and the copy and the comparison, and you'll never get to it. Right? I don't know. I'm confused. Sorry.
So when we say we choose a dimension, say we choose D = 3. Yeah. So we will only encode a superposition of these LP modes. So we don't actually use the other L's or other P's. We just use superpositions of this one, and same with the second SLM. So it's almost like we limit the superpositions to this one. So how does that translate to another physical system? You probably have to, like, I don't know, suppress population, for example, if you were doing energy levels, like, I don't know. But so for this one, we define this.
Yeah, what I'm saying is maybe there could be, one could think of a different distance measure, which is not necessarily an overlap. That would again give you a distance, of course, in that appropriate space. But then that might even turn out to be interesting because it might guide you towards even the LNP values. I mean, in some sense, rather than beginning with the set that you already know. What I'm trying to say, let's say begin with unknown LP. The
coefficients for the 0, 1, 2s, but for what the 0, 1, 2s are.
Yeah.
Okay, I see. So
does it make sense, or I mean, or might be a more difficult problem?
It's a more difficult problem, definitely. Like we haven't tried it.
Yeah. What I'm saying is just the dimensionality, knowing, of course, is a nice thing. Yeah, if you choose it less, you get some zeros. But then if you really want to, mere dimension is not enough. You need to know a little more of what forms that set D.
Yeah, but yeah, so we didn't try it because if you really talk to these theorist people, like some of you probably are, like they actually didn't care
Jackie,
what the 0, 1
Jackie,
are.
by the way, Harsha is a theorist, so just be.
I'm being careful here.
I'm a cleric to the turncoat, so don't worry about it.
Yeah, so 0, 1, and 2, they didn't care. Like they say for as long as it's an orthonormal set, like they didn't care what the L's and P's are.
Correct.
So it wasn't a problem that we tried to like define and solve as is, just because to them it was 0, 1, 2, and they didn't care what those were. But yeah, you're right. Like, you have a physical system where it would be interesting to find what is 0, what is 1, what is 2, and that's.
Yeah, but probably tomography by definition just finding the coefficients. It is not necessarily finding the basis per se. Yeah, so I understand that. Maybe it's a much tougher problem. Thank you. Very enjoyable talk. Thanks a lot.
Thank you.
Okay, other questions? So Suman, you said you have multiple questions. So was that all, or do you have more?
No, thank you very much.
Okay.
Only just one another question I want to ask, that regarding L and P modes, the question arises, so that when the state has been measured, is that the superposition was created with different L and same P, or any LP superposition?
So we define what L and P are. So for example, here for the qubit, like, let me see if I could. So for example, here, if we were doing a qubit, we only do superpositions of -2, 0, 0, 1, and 2, 0. So we have these indices defined.
I see. Okay. Thank you.
Mm-hmm. But you could do any superposition of the the basis vectors, right? The basis shapes.
Yeah,
so
we
to
could
say.
do any superposition of the basis vector.
Mm-hmm. Mm-hmm. Okay.
I mean, it's not just Laguerre-Gaussian modes as well. Like you'd find a lot of papers talk about Hermite-Gauss modes. Like there's recently these perfect vortex states, which actually sound interesting as well.
Mm-hmm.
Yeah,
No, but for any tomography, you do have to define the basis states. So I mean, if the basis states change, the thing will change. Yes. Okay. And what you're probably, I missed it. What exactly are the difficulties for extending this to mixed states?
Because the mixed states that we have, so the SLM would produce only a pure state. And so it would, like, right, you display a hologram, it will give you a particular shape. To do a mixed state, you need to add a coin. Like you toss a coin between this value and this value, prepare this one, this value. Like, so you've got that, I don't know, that added step of tossing a coin and then preparing something, and you need to sample you need, in order to get a distribution, you really need to do that a lot of times. Like you won't be able to say, if you toss the coin 2 times and you're working on a 3-dimensional space, it's not enough. You have to toss the coin many, many times. So for the algorithm to work for the mixed states, we just had to do some iterations that would give you that distribution well first before the algorithm can start looking for that density matrix.
So that is just a generation part, right? I mean.
Yeah, the generation.
So suppose if I give you some mixed state that you do not have to generate, then the algorithm just works. For example, if you have down conversion, if you take just one of the outputs, which are kind of like.
Yeah, it should work. We haven't tried it yet.
Okay. Yeah. Okay. And then.
Hello, sir.
Yes, Srimasu, go ahead.
I have one more question. In the same self-guiding tomography, with compared to standard tomography, is this technique helping in reducing the number of measurements on the multiple copies, or what is the, converging the fast to the coefficients?
For the standard tomography, for example, if you measure so if it were a pure state, for example, for a qubit, you just need 6 measurements. And you could get the Stokes parameters, you could get the density matrix from that. So I don't think it helps in reducing the number of holograms you display on the SLM. What it really gives you is that you don't have to do any post-processing, and you could leave it for as long as you want, and you'll get the infidelity that you want.
Okay, thank you. One more question. Hello?
Yeah, go ahead.
In the first part, ignorance part, so whether the teacher is asking whatever question, the student has the same probability to answer a given part is known or unknown in the quantum encoding. Is that means quantum encoding is secure? Or what is the conclusion you are giving in the first part?
I tried to be mysterious about that. So in the ignorance experiment, you find if you do the quantum encoding, you get uniform guessing probability, and that's weird. What's the implication on security? So the min-entropy splitting inequality is actually used for security proofs. Like when they do provable security, they use the min-entropy splitting inequality. There are some proofs that use that, and they take it as true. So with this experiment, what we're saying is that you cannot use that inequality when you're trying to prove security, because it doesn't hold for a quantum encoding. Like if you have a communication system and there is information leaking out of it, it could be classical information or quantum information. So if you have classical information leaking out, like the encoding, the cheat sheet, then okay, that would be safe. But if you have quantum information leaking out, you could not use the min-entropy splitting inequality because it does not hold for quantum information. So I'm not an expert on what security proofs are out there that would be invalidated by this, but that's as much as I know. You cannot use that to prove security anymore.
Okay, thank you very much. Very nice talk.
Any other question? Well, I have one more. So is there any limit to what dimensionality can you can handle with this? I mean, 3, 4, 10, 20, 200.
So the physical system, we have an experiment with colleagues over at engineering. I was just talking with them this afternoon, actually. So in that system, we could handle up to 59 modes. Mm-hmm. And it's limited by the size, really. And
size of the generation part, or the size?
Yeah, the size of everything. The size of what you could generate and what you could measure. Mm-hmm. And things really get things get bad quickly as you increase the dimensions. It could, because the patterns become more complicated, it becomes harder to align. Like Marcus could tell you how more sensitive it was when we went to the 20 dimensions. It's just harder when you go to higher dimensions, but it's definitely possible to go to a big number.
So the fidelity decreases as the dimensionality increases, or there is no, it's just that if you can manage, you can maintain the same fidelity even with the higher dimensions?
I don't know, what do you think, Marcos? We do have less fidelity for the 20 dimensions. Like it's about 96-97%, which is still good. I think you'd hit a bit, I would say.
So I'd say two things. So the first thing is, the higher the dimensions get, the more crosstalks you get with adjacent modes. So let's say if you encode your information in, like your logical 19 is a mode with L equals 19, and your logical 20 is a mode with L equals 20. There's a lot more crosstalk there, so it becomes harder to, because they're very similar. Whereas between 0 and 1, there's not a lot of crosstalk. So as you go to higher dimensions, you need to use higher and higher L and T values. So that's why you see it on the slide now. That's why we go to negative ones as well, because like this, we can keep the space smaller. So we here, for example, for the QuIC, we go from -4 to +4. Whereas if you go just the positive direction, you have to go to +8. And then the other thing is, in principle, you still have to wait longer. So you're gonna probably get some issue, like you can't get whatever 5 nines in fidelity for qubits anymore because of technical reasons. But if you wait, I don't know, like what we've shown you is like 600 iterations, but if you wait 2000, you still get further down. So you can get closer and closer. But it would take, for higher dimensions, it would just take longer, because these random steps that you take, there are just a lot more possibilities of doing a random step in a 20-dimensional system than doing a random step in a 3-dimensional system.
Okay. Yeah, because this was I was thinking that in your system, I mean, ultimately the detection is just that of the photon. I mean, you're not detecting any spatial pattern that you would be limited by the spatial resolution of the camera. So and again, you're probably limited to some extent by the generation part as to how precisely the SLM is able to produce the state that you want to produce.
So it's essentially, Anand, you have to match generation and measurement. So how well could you align those two patterns such that you are actually able to convert your shape back to a single mode that will then go to your fiber and to the detector? And that becomes more sensitive as you go to higher dimensions. And as Marcus mentioned, you also have, in theory, all LG modes should be orthogonal, but in practice, there is some crosstalk as you go to higher dimensions.
So I guess
Second, go ahead.
on this, you are also limited then by the dark counts, no? Because as you go to higher dimensions, it will be difficult for you to resolve like neighboring modes. That is fundamentally limited by the dark counts of purity.
We haven't hit that wall actually for the high count case that we had, just because our dark count is actually very good. I think we have 100. Is it 100?
But regarding this also, I just wanted to ask whether your higher dimensional beams are closer to naturally being mixed state because of this crosstalk.
Yeah, probably there's some mix. You get less purity as you go to higher dimensions. Yeah, probably.
So, I mean, follow up on that question. So would it be better that you don't generate your state and just use what you have naturally available? For example, down conversion, if you just use, one of the signal or idler, would you, I mean, you then have more than 200 dimensional state. And I mean, if you can demonstrate that, you don't have a generation problem there. And if you can
have a generation problem. Yeah, it's just that we don't, if you have, so you herald on one photon of the down conversion.
You don't even need to. We know that you don't even need to herald. Just throw away the other one. And if I just get the signal, we know it's a mixed state. And we know exactly what the state is. If I.
So you know that one arm will be a mixed state, and you just like display as many modes as you want
Yes,
on
yes, yes,
the
yes.
SLM.
Yes.
Yeah, okay, we haven't tried that.
Okay.
But it will be very high dimensional, Anand. It would be a very high dimensional
Yeah,
state.
about 200 dimensional. Well, one can squeeze it by changing the phase matching, but 50 dimensional, 100, I mean, if you have thicker crystal, you can reduce the dimensionality. But you can easily get 50 to 100 dimensional, and you're getting for free without you doing anything. And it's a mix.
Yeah, you get it for free. Yeah, that's true.
Mm-hmm.
Yeah, it's just a very big space though to hop. Like, have you done it?
Well, I have measured it, but not the full state, just the diagonal entries, just the diagonal entries of the mixed state. But,
Diagonal, okay. Oh,
yeah,
that's
so I have seen it up to about 250 dimensions.
250 dimensions.
For 2 millimeter and slightly non-collinear, it is about 250 dimensions. Yeah, dimensional state, yes. So,
and what did you use to measure? Like, you just use LG modes, HG
no,
modes?
we developed a interferometer based, I mean, not as versatile as yours, but develop a interferometric meter based this state tomography. But that state tomography is not that it can do the entire density matrix, but it can just get the diagonal states.
Get the diagonal.
Yes,
I see.
yes.
Okay.
So by just measuring the diagonal state, you can get an idea of how big is the Hilbert space. And we have seen that for down conversion, 2 millimeter crystal, slightly non-collinear, it can go up to 250 dimension. If it's collinear, it's about 100 dimension. If you make the crystal thicker and collinear, it's about 50, 60, 70 dimension. So
that would be interesting. So I actually have in my lab a 5 millimeter crystal right now, and we're slightly non-collinear.
So if you have 5 millimeter, and if you make it collinear, I think you are less than 100 dimension. I mean, this is what I would guess. Yes. Yes.
Okay. I'll look up. Maybe I'll email you about that.
So we have seen a few. So is there anything else to be done in the tomography? It seems like you have done it all. There's nothing left.
I think a lot of people are actually interested in the, no prior information tomography, which like, I don't know. It's a very difficult problem. I actually don't know if it makes sense.
But then you are not assuming any a priori situation, anything, right? I mean, you have an unknown state coming in.
In this case.
Sorry, what was that?
Like, we assume dimension.
Oh, the dimensionality. But let's say if you take the dimensionality to be 100, that will pretty much cover all the states that we typically get.
Yeah. Okay. Well.
In that sense.
Yeah.
Excellent. Excellent. Okay, so I think maybe I can have one last final question. Can you think of a two photon version of that your ignorance experiment you did? I mean, your thing is either the weak coherent state or one photon is the same thing.
So it is. So I actually thought, a two version experiment. I haven't thought about it yet, but I think it would really be interesting.
Okay.
Yeah, I found it, these entropic inequalities, I think they're becoming, a lot of people I think are becoming more curious about them recently. Yeah, but if you think of a 2 photon version, like, we could do it.
Okay, we can think about it. Okay, so any other question we have for Jackie? I think we have asked her enough. Any other final question? Well, if not, Jackie, we would have clapped for you, but I think I'll clap on behalf of everyone, everyone over here.
For coming. And I hope you're all doing well despite the pandemic. Like, this is something that won't happen if we didn't have COVID. So at least it's something good coming out of it.
That is absolutely true. That is absolutely true. Yes. So yeah. So Jackie, thank you so much. And I think we'll put this on YouTube, and I'll send you the link, and which you can.
All right. Okay. So. Thanks, Anna, and thanks everyone for coming.
Thank you so much. Okay. Bye bye.